Kia ora Year 12. In this video I'm going to look at how we can use partial fractions to solve integration problems. So this is the follow on from the work we did early this year when we just learnt how to break things up into partial fractions. But now we have a purpose for doing it. One thing I'd like to know is if there are sound quality issues with this video, because there were with one of the ones I did at the weekend. So please, if there are, could you quickly send me an email and let me know that you can't hear very well. Isaac, I'm relying on you to do that. So here's the integral that we're going to figure out. We want to integrate this. So 7x minus 2 over a pretty yucky denominator. So let's first of all look at that and see if it fits the general pattern for integrating a function and getting a log. Now, this here is a cubic, but my numerator is not a quadratic, so I don't have the pattern of this. All right, so we know that it's not going to be a straightforward one. So that tells me that what I'm going to do is I'm going to move away from the integration, and the first thing is to break up this into the different bits. So really this video is revision of all of that partial fraction stuff, but it's been a while, so let's get into it. We've got a repeated factor in the denominator, so I'm going to do this to generate the 3 bits. So 3 little fractions, and this one here is going to be 2x plus 3. Right, now you might want to pause the video now and just see how much do you remember of what we do next. I'm going to do that on the next slide, and then finally we'll put it back together and do the integration, which is the easy part. Okay, so cross multiplying and just looking at the denominator, we get 7x minus 2 is always going to be equal to this. Alright, so I'm just cross multiplying and working through my A, B and C. Oh, something's gone funny there. There's the bracket that I need. Okay, so we should get that. Now the first couple of things we're going to do are we're going to substitute in values that are going to get rid of a bunch of terms. So we start by saying let x equals 1, because that's going to clear out those two. Substituting that in, we get 7 minus 2 is equal to 0. Right, that's going to be 0 because of x minus 1, plus b times 2 plus 3 plus 0, because that will work out to be 0. So that generates 5 is equal to 5b, and that gives me b equals 1. Right, now we do the same thing with the next value that's going to give me some 0 terms. So we want to substitute in x is negative 3 over 2. So we'll do that in blue. X is equal to negative 3 over 2. The substitution's a bit yuckier, but we'll get there. So 7, well, you can do this, I'll stop talking. Okay, so I'm working all of that out. What do we get? Well, we've got negative 21 over 2 minus 2 is equal to 25 over 4c. Cleaning that up gives me, I'll just squeeze it in here, negative 25 over 2 equals 25 over 4c, and c must equal negative 2. So we've sorted out b is 1 and c is negative 2, but we still have to get a. So the clue I'm going to give you before you try it is matching coefficients. You can match on either the x squared term, the x term, or the constant term, but I would probably pick the x squared term. So have a go at that, and I'm going to go through that on the next slide. Alright, so we've got 7x minus 2 is equal to a times this. what's left? A plus b, where are we? B times 2x plus 3 plus c times x minus 1 squared. Right, so that's the first bit. And now what we're going to do is we have to figure out a. So we know that over here we've got 0x squared hiding in there. So we must have 0 equaling the coefficient for all of the x squared terms over here. So 0 must equal 2a, because this expands to give me 2x squared times a. There's no x squared stuff going on in there, and there's a cx squared there. So we've got 2a plus c, but we know that c is negative 2, so we get 2a minus 2, and so a has to be 1. So now we've got all of them, we can finally get on to doing the integration. So hopefully what I want you to see is that the hard work here is not in the integration. So that's coming on the next slide. Right, so we break this up now at last. I'm just going to cheat and put those in there like that. Please don't do that when you're writing it in your book. And now we've got 1 over x minus 1, big bracket to start, plus another 1 over x minus 1 squared, minus 2 over 2x plus 3, integrated with respect to x. So taking that one step at a time, we see that now we've got 3 really straightforward little integrals. This one's going to give me the natural log of x minus 1. This bit is going to give me minus x minus 1 to the negative 1. Right, so that's just the power rule, and the derivative of the inside function is just plain old 1. So that bit's all right. And lastly, this is going to anti-differentiate to give me minus the natural log of 2x plus 3 plus c. Now let's just check why this is going to work to give me that. And it's because the chain rule, when applied to this, gives me a derivative of the inside function of 2. And that's what we've got going on up there. So that all works quite well. Now that's fine to leave your answer like that, but a prettier version goes like this. The log of x minus 1 over 2x plus 3, using my log rules from level 2, minus 1 over x minus 1 plus c, that's a tick, or the answer in the back of the book, almost the same, is this. So it's going to be plus 1 over 1 minus x plus c. Alright, that's all for now. That's just one example done, but the ones in 8D are all much like that. There are about 3 other pattern types you've got to remember from partial fractions. So if you can't remember them, go back and find the partial fractions videos. Thanks for watching.